Hello, everybody. It's Sunday, and I'm giving you a lecture for Monday morning, Lecture 31, on Chapter 6 of Thermodynamics 3331. It's a snowy day outside and Easter. It's I guess this is what you come to expect in Minnesota. It's pretty typical here, I guess, but still always a little depressing to see a snowstorm on Easter. But okay. Let's get going on today's lecture. I want to do a little introduction here, of course, as I usually do, by looking at the survey from last class. I don't really have any further announcements. I mean, everybody has been doing the homeworks and keeping up with the discussions, and we all know that there's an exam on Thursday. I know that most of you have a very busy week in terms of exams and other things, but I'm really sorry about the timing of this exam. It's not ideal, I know, especially considering that you have other classes that you're going to have exams in this week. But hopefully everything should go fine. You've been doing a pretty good job with this class and keeping up with it and asking questions. So hopefully things will go well and the exam will go well. Okay, let's see. Let's look at this. Okay, so for the survey question from last Friday, oops, I did a little typo on this one. For a adiabatic process from state 1 to state 2, sigma represents what? Okay, the answer was clearly A, the entropy production of the system. We said that sigma represents the production of entropy for a system. The entropy consumption of the system generally, it could represent the consumption, but generally we talk about it as energy production of the system. Sigma cannot be negative. So sigma has to be positive. So it means the entropy or zero for a reversible system, which means that essentially the entropy consumption is not really something we talk about. The heat transfer to the system looks like maybe one or two of you decided to put that in there. It's related to the heat transfer of the system because in the second law entropy balance, heat transfer is in there in the equation, but that's not what it is. And we'll talk a little bit more about the equation today. And the fourth one is the work accomplished by the system. So as I said before, work, you can relate work to the second law, but in the second law entropy balance, work doesn't appear. It's only related to the amount of heat transfer that's going through across the boundary at some temperature. All right, so you pretty much have it here. I'm going to keep on going with the lecture here, and hopefully we can get through Chapter 6 before the exam. I don't know if we're going to get through all of it, but I probably will because we've actually covered, I'm on slide 26 of 66. But actually, if you look at the slides for the rest of the Chapter 6, you can see that it's all about trying to find the change of entropy for different gases and stuff, and we've already been doing that. So you can look in the equations that we'll be using, or we've been using, are in the back of the slides. So I recommend, being that it's Monday tomorrow, that you actually go through the rest of the slides right away. Don't wait for me to cover them in a lecture. Just start paging through them and looking at it. You'll see some familiar things. For example, you'll see, just to give you a little preview here, if you go through the slides that are posted on Canvas, you'll see here, let's see. So entropy change for an incompressible substance, you recognize this equation. You might recognize these equations, the Cp delta T R ln V2 over V1, which is an example, which is a equation that I gave you on the homework assignment. So this other one also for an ideal gas, Cp dt over T R ln P2 over P1, the pressure correction factor. You've used this before. So you've also seen this one, the S naught. So this was also something that's in the back of the slides and something we've already used. So what I'm saying is the rest of the slides really aren't that new. There's some new stuff in there that we will cover, but I'll just kind of blow through them on Wednesday's lecture. Today, the most important thing that we cover is talking about energy rate balance for closed system and for a control volume. Now, it's not that difficult, really, to extrapolate what we've been doing for closed systems into control volumes. It's not a really big deal, not a huge leap. So on a time basis, we've at the start always with putting the entropy equation or putting the entropy balance into a rate expression, and that's just by saying ds dt, so dividing everything by dt. So big S, big ds dt is equal to the sum of the heat transfers rates. So QJ, that would be in kilowatts, QJ dot, over some temperature at which those heat transfer events occur on the boundary, plus the sigma dot, which is the rate of entropy production. So that's the entropy loss of the system. Production of the system going out to the environment. Okay, so the time rate of entropy production due to irreversibilities within the system. Okay, so these are this is the rate equation. I mean, it's very similar to just the non-rate equation. It's just the divided by dt, because the q dot and the sigma dot are just the rates in and out of the control volume. So here's just a simple example, energy rate balance for a closed system. So this is an example that's in the slides that you can kind of work through yourself if you want. An inventor claims that the device shown, which is, I don't know, some magic box, generates electricity at 100 kilojoules per second, which you know as a kilowatt, while receiving heat transfer of energy at rate 250 kilojoules per second at temperature of 500 K, receiving a second heat transfer at a rate of 350 kilowatts at 700 K, and discharging energy by heat transfer at 500. Oh, it's just doing all sorts of heat transfers of different things. Looks like it's got some, let's see, what's going on here? Oh, it's receiving electricity at a rate of, okay, that's the electricity that you're seeing here on the right. I'm not paying attention here to the problem. Okay, and then each heat transfer is positive in the direction of the arrow for the operation at steady state. Evaluate this claim. So essentially what they're trying to say is that the device that this inventor has created generates electricity generates 100 kilowatts of electricity by receiving and rejecting some heat. Okay, first off, you have to think to yourself, if you're the patent examiner on this patent and you're looking at it and you go, well, okay, so the box takes heat in, rejects heat, and also produces work. So you would say, just from the outset, it doesn't violate the Kelvin-Planck statement, right? Everything is fine. I wouldn't say that it doesn't. You can't really say that it doesn't totally violate the second law, but it doesn't violate the second law kind of in principle. It certainly doesn't violate the first law, and you can check that. You can check that because you have all the heat streams. So if you just know, just from the top of your head, we can look here and we can see that it's 250 kilojoules in, 350 kilojoules in. So there's 600 kilojoules per second. So 600 kilowatts of heat is going into this thing, this magic device, engine, fuel cell, whatever it is. And it's losing 500 kilojoules plus 100 kilojoules of work, so 600. So the energy balance is working. So by the first law, as the patent examiner, you say, okay, well, the claims, the heat transfer is all balanced. So there's something going on right with this system. So now we want to evaluate whether this system is possible based on the second law. So okay, oops, I moved myself again. Okay, so here we go. Let's do it. So entropy balance for the closed system. So now we're going to do this is the energy balance, and so clearly this chord is in accord with the first law of thermodynamics. We already talked about that. We did that in our head, so we didn't need to write that down. It's clear that all works. Okay, applying an entropy rate balance, then you can say ds dt is equals 0 equals this thing plus some generation. So just think that it's a cycle. I guess they say it was a cycle? Hold on. A device shown. I guess they're just assuming that it's a cycle. Okay, that it starts and ends at the same thing. I don't know, that's kind of interesting. We're assuming that it's a cycle. I don't know. Is that really what it is? But okay, so say it's a cycle. All right. So then the ds dt is 0 because it's starting and ending at the same state within whatever thing it's doing in there with all the heat transfers at these different temperatures. And you notice that you're just accounting for the heat transfer here, not the work, and then you get a sigma. And then you solve this thing for the sigma, 250 over 500, 350 over 700, 500 over 1,000, and you get these negative 0.5 plus 0.5 times minus 0.5 kilojoules per second per K, and you get negative kilojoules seconds per K. Uh-oh, bummer. So this means that essentially they're extracting too much work for how much heat transfer they're putting in, because you have negative 0.5 kilojoules per second K. So it's a violator of the second law. So it says, since sigma dot is negative, the claim is not in accord with the second law of thermodynamics and therefore is denied. Okay, so you have to evaluate it. So it doesn't necessarily violate the Kelvin-Planck statement, right? It definitely doesn't violate the first law, but it violates the second law because it's extracting too much work for the amount of heat that it's transferring in and out. And that's what's going on here. So, yep, that's the way it is. Okay, anyways, rejected. Okay, next. Now, this, of course, the rate equation leads us to the entropy rate balance for control volumes. So it's 5 slides here. I'm going to go through them quickly, and then we're going to do an example problem or two if I have time. So what we've got here is, like mass and energy, entropy can be transferred into or out of a control volume by streams of matter. Since this is the principal difference between the closed system and the control volume entropy rate balances, the control volume form can be obtained by modifying the closed system form to account for such entropy transfer. Just like you could have energy transfer across the boundary, you can also have entropy transfer across the boundary. So you have to take into account the change of entropy for the control volume itself, big D big S dt, right? For the control volume, that's why they put the little CV here, equals the sum of the Q dots over the temperatures at which they occur, which is the same as what we've been dealing with. Now, just like when we did the energy rate balance, we have to account for the entropy rates of entropy transfer. So m dot I SI, the sum of m dot I SI minus the sum of m dot E SE, so I think's leaving, the entropy coming in, the entropy going out, plus the entropy rate of production. Now here's something interesting. Remember how when we developed the control volume form of the first law, we had to account for the enthalpy because we had flow work. Remember the flow work, which is the pressure on either side? Good thing to remember for your exam, by the way. So in this case, we have SI and SE, which is the exact same as what we had before. Since work doesn't show up in the second law entropy balance, we don't need to account for flow work in the second law. I'm hoping that if you were in class and we were talking about it, one of you would ask me that question and I would answer it and seem all smart. Okay? But essentially, that's what's going on. We don't have any flow work because work doesn't show up in this equation, as we had said. It doesn't show up implicitly in this equation, right? Of course, you can find work and find the ideal amount of work. But in this case, the second law equation does not account for work. Okay, so now essentially we've added it onto our entropy balance and we take into account the entropy coming in and the entropy coming out. Okay. Let's see. Let's move on. All right, so now we have, I'll move myself over here. For control volumes at steady state, we have, of course, the steady state entropy balances would be 0 because the change in entropy at steady state for like a turbine, for example, is 0, right? It's just like the change in energy for that thing is 0. Like the control volume isn't changing its state. The state is totally the same all throughout it. So it's uniform inside. There's flow going in and doing something and coming out. So in that case, the control volume entropy doesn't change, but all we have left is the in and the out. The entropy coming in, entropy coming out. So there's still entropy generation. This sigma dot still exists, but we don't have to account for it. Now you can also, for one inlet and one outlet, you don't have to put the sums in, which is nice. But you have to have the sums for the energy. So there could be heat loss from different parts of a turbine or a compressor or whatever. So you have to incorporate the sum. So this sum right here has to still be there. The m dot S1 minus S2. So now we have the single inlet and single outlet 1 and 2 respectively, and we have still the entropy production rate. Now, of course, what I can guess what they're going to do next. What we're going to do next is do a little example here where we talk about it a little bit. Okay, so this is what is this thing? It's a valve, you see? Oh, it's a really nice valve. It's a lot better than any drawings that I make. It's nice. Okay, here we go. example, water vapor enters a valve at 0.7. I put myself down here. There we go. Water vapor enters the valve at 0.7 bar, 280 degrees C, and exits at 0.35 bar. So it makes sense. It's a valve. It's lowering pressure, right? If the water vapor undergoes a throttling process, determine the rate of entropy production within the valve in kilojoules per K per water vapor flowing. Okay, what's the source of per kilogram? So it's kilojoules per kilogram K. What's the source of entropy production in this case? Okay, well, first of all, it's a throttling process, so there's no heat transfer. All right, so they're assuming essentially for a throttling process, it's adiabatic. It didn't say that in the problem, which is a little suspect. I would mostly tell you whether it's adiabatic or not. But in this case, they assumed adiabatic, and they got rid of the Q term right here, where they say it goes to 0. And you're left here with m dot S1 minus S2, which is the inlet and outlet, and the sigma dot, which is the entropy production. Okay, so let's see what happens here. So there's no heat transfer. Where's the entropy going? All right, sigma dot over m equals S2 minus S1. You find out if you look in there, you can look at the quality. Oh, excuse me. Oh. Okay, you can look up the quality, 0.7 bar, 0.7 and 280 C. Oh, I bet that's actually superheated. I bet you just based on my table A4, right? Superheated. H1 equals 3035 and S1 equals 8.3162. And then interpolating through a throttling process, it's isenthalpic for an adiabatic throttling process where H1 equals H2. I would really recommend reviewing that equation from our last chapter when we talked about control volume. 2 chapters ago, chapter 4, control volume analyses of different devices. So we remember that the throttling process is generally considered isenthalpic, meaning H1 equals H2. Okay, so then we just go and take H2 and find H2 where H1 and at the pressure that we had, and we get an H and get an S, and then we can of course calculate sigma. So sigma dot control volume over m dot is then given by the following. The difference between the enthalpy in and out gives you 0.3133, which means that you have sigma dot, which means you have entropy production. And then if we think about the irreversibilities that we've talked about in chapter 5, the source of the entropy production here is definitely the unrestrained expansion to a lower pressure undergone by the water vapor. All right, so how is this, the one thing that's interesting, right, is how is this entropy manifest, right? I mean, there's no heat loss, there's no work, so there's nothing else that comes out except the stuff in and the stuff out. The point is that the enthalpy is the same since it's isenthalpic, but the entropy change is controlling the pressure drop. Now, we didn't really talk about the pressure drop. We just showed that it was 0.7 bar drop to 0.35 bar. Now, if there was more or less entropy, the pressure drop would change. The temperature drop would be the same because H1 equals H2. Well, not necessarily, because H1 equals H2 at the same pressure, so then you'd have to relate the pressures. But the point is that the entropy is not affecting the heat transfer, right? You're saying, well, where does the entropy go? Well, how does it affect the process? Well, the process just is affected because you have more pressure drop. You just drop more through the valve, and the valve it becomes has a lot more loss or pressure loss, right? And so you're kind of losing something. You're losing the entropy. The energy stays the same in and out. It has to, because by the energy equation, the energy has to be conserved. But the entropy does not have to be conserved per se. You can generate it. And that entropy production eventually goes to disorder of the universe and ultimate chaos. That's a nice thought on Easter. Okay. All right, let's go. Let's keep moving. We're already 20 minutes in here. So what we're going to do now is... they have some comments too, beyond my cheesy comments about the end of days here. It says, comment, the value of entropy production for a single component such as a throttling valve considered here often does not have much significance by itself. The significance of the entropy production of any component is normally determined through comparison with the entropy production values of other components. combined with that component to form an integrated system. So, reducing irreversibilities of components with the highest entropy production rates may lead to improved thermodynamic performance of the integrated system. Okay. That means that if you put this valve in some system, right, and you say, oh, wow, I'm losing a lot of pressure in this valve, I could be recovering that pressure in a turbine, then probably it'd be better to have a different valve that didn't drop as much pressure, that had less throttling loss. Okay. Valves I don't really think very much about. But I guess you think about a turbine and you have a lot of entropy production in a turbine. You want to make sure that you are accounting for that, and we look through a second law analysis would find those things, find those irreversibilities. So that looking at all the sigma dots of all the different components within a steam power plant, for example, could help you identify where the highest rates of entropy production were, therefore find the most inefficient systems that you have. All right, so fair enough. All right, so let's go to the next slide where now we're going to talk about, then we're on to our example problems. Good, that's fine. So we can spend the rest of our time doing some examples on these things that help you guys out. So the first example, let's see, I have two examples. I have one with steam and one with air. Okay, so the first one is entropy and control volumes 1. Okay, so an open feed water heater is a direct contact heat exchanger used in vapor power plants. Shown in the figure, are the operating data for the open feed water heater with H2O as a working fluid operating steady state, or ignoring stray heat transfer from the outside in the heat exchanger to its surroundings. So that's always a good sign to call it adiabatic, right? And kinetic and potential energy effects determine the rate of entropy production in kilowatts per K. So the sigma dot, find the sigma dot. All right, so let's do this problem. Now we have a feed water heater that, an open feed water heater is a device that is typically actually used. So essentially when it's open, what it means, it's not like a heat exchanger, it's a mix. They're mixing, so they're taking a stream here at 3 bar and high quality, and you've got 3 bar and low. This is pretty high quality stuff, 3 bar 0.92, and you're taking a little bit of that high quality steam and you're mixing it with water, and you're coming out with some saturated liquid at preheated saturated liquid at the same pressure. So notice that the pressure drop isn't changing with this system. Each of the streams has 3 bar. Okay, so let's go to my example problem solving here. All right, so what do we have? So we have an open feed water heater. With known properties. No, we'll just say inlet and outlet. What we're supposed to find is ignoring the heat transfer, find the turbulence. So we're supposed to find sigma dot. We're supposed to assume here. First of all, we're assuming that it's adiabatic. We're going to assume also that it's steady state. What else? 3, we're going to assume no delta KE and PE. All right, so there's so there's no like high velocity, or the thing's not going from very high altitude. And steady state, and it's water is the working fluid. Okay, so let's see. Let's make some diagrams here. I'm just going to use the diagram that we have. I mean, this is my thermodynamic system. So I'm just use the diagram that I'm not going to redraw it. We have the states, as you can see here. And so we're going to call this my control volume, CV. All right, so I did that part. But the other diagram that we always like to make is the TS diagram. So let's make the TS diagram. Maybe I'll just make it here, and I'll change its location in a minute if I need to. So TS diagram is here. Of course, we have the vapor dome. and we have, because we have water, saturated water. Notice that it gives us sort of saturated liquid. So when it says stuff like that, you know it's got to be steam. You just put the vapor dome in, okay? You know it's a vapor dome. So everything's operating at the same pressure. So that's nice. So we have one isobar at 3 bar, right? Right? So everything's operating along this line. So we know that state 3 is saturated liquid. So this is state 3 is there on the left. Let's see. Now state 2. Let's see. State 2 is the stuff coming in with 0.92 quality. So 0.92. So this is state 2. And state 1 is 3 bar 36 degrees C. So that must be like down low. That must be like over here somewhere. So state 1 is low quality water, essentially. Just water at high pressure water, relatively high pressure water at 36 degrees C. 36 degrees C is still pretty hot, but I mean, it's close to room temperature, right? Okay. All right, so it's kind of like lukewarm water. Now, let's do. So we have 1, 2, and 3. So we have 2 plus 1 is going to 3. We're making saturated, we're making water that's ready to go into a boiler, essentially. That's why they call it a feed water heater. So the feed water heater is just ready to go. So it's water that the sensible heat is already taken up. The sensible heat would be the stuff to heat up the water, right, to get it up to the boiling point. And then once it's up to the boiling point, boom, it's starting to boil a lot better inside your boiler. So that's why they use the open feed water heater concept in a power plant. So we're going to assume here that for state 1, we're going to assume that H at T, we'll just say H1 is equal to HF at 36 degrees C, which if you look in the tables, it's 150.86 kilojoules per kilogram. S1 then is also SF at 36 degrees C from the table I don't know. I think it's table A2. I think it's table A1. Oh man, I don't know. Let me just go check it out. I don't want to waste time, but I don't want to also say something wrong. So I believe we're talking about table. Here's the textbook. No. Where's the textbook? Here it is. Okay. So the textbook is here. I'm moving myself over here. And then we'll find out what table we're looking for the temperature table. Bear with me here. Get to it. SI tables. Here we go. Temperature tables, table A2. 36 degrees C is right here. Okay. So yeah. So you can see that it's right here. Oops. Table A2. 36 degrees C is right. It's not letting me highlight it. Whatever, you can see it here where my arrow is. Okay, so now, 36 degrees C, so this is table A2, the temperature table for water, and then SF at 36 degrees C is 0.5188 kilojoules per kilogram K. Okay, so then we've got that. Since we have all the states, we can just look at all the states, right? I think we know what they all are. State 2, we know state 2 is saturated. Saturated, high quality, saturated state 2, high quality saturated steam. We have H2 equals HF2 plus X2 HFG2. And this is evaluated at the pressure that we have at 3 bar. So we're using table A3 in this case because we're using the pressure table. And we know that S2 also is SF2 plus X2 SFG2, which is the difference between HSG and SF. So if you do these and plug in the numbers, which I'm going to not plug all the numbers in. Well, maybe I will. So I have the numbers. So H2 equals 561.5 minus 0.92 times 2725 minus 562, which is what we have there. And this is equal to 2552.2 kilojoules per kilogram. And then S2, I'm just going to give you the number. You can look this up too. This is 6.5663 from this equation. Okay, kilojoules per kilogram K. All right, so we have those. Now let's do. Okay, so then let's go state 3. I find it sometimes if you know what the thermodynamic states are, just look everything up in advance and then just solve the problem. So you don't have to like go flip back and forth to the book or flip back and forth into the computer notes and find out these numbers. Just get everything out of the way. So state 3 is saturated liquid. State 3 is saturated liquid. So it's H3 equals HF at 3 bar. Which is 561.47, and S3 equals SF at 3 bar from table A3. And you have here something low, 1.6718 kilojoules per kilogram. Okay, so now we've got all the numbers we need. So we apply the mass and energy balance. So let's see what we're going to do. Mass first. I mean, it's pretty obvious. So it's m dot 1 plus m dot 2 equals m dot 3, right? Because the change in mass. So dmcv dt equals 0 because it's steady state. Okay, the energy balance goes something like this. So 0 equals q dot minus w dot plus m dot 1 h1 plus m dot 2 h2 plus minus m dot 3 h3. And so we know that we're going to end up getting all kind of, these are guys are going to go to 0. This goes to 0 because there's adiabatic, right? First of all, adiabatic, as we said. And there's no shaft work, so the work goes to 0. And so you're going to end up in an equation that looks like the following. M dot 3 minus m dot 2 h1 plus m dot 2 h2 minus m dot 3 h3 equals 0. All right, so now we got a bunch of m dots in here, 2 and 3. So we got rid of m dot 1. So get rid of m dot 1. So now we have combined heat and energy equation. And so now we're at the point where we don't really know the entropy production unless, we have to do the entropy balance, of course. Let's see, we can probably find, do we know what one of the mass flow rates? Yes, we do. Oh, we know m dot 3. So we can find m dot 2. So let's find m dot 2. So m dot 2, where are we? Or m dot 1, I guess. Or we can find any of them. We can find that m dot 2 and m dot 1. M dot 2 is equal to m dot 3, and then you just do algebra here, h3 minus h1 over h2 minus h1, and you end up getting, so 80, and then you have 561.5 minus 150.9, which is h1, and you get 2552 minus 151, which is the other H's that you needed, and you end up getting 13.68 kilograms per second. And then m dot 1 is equal to m dot 3 minus m dot 2 by the mass conservation. And this ends up being 66.32 kilograms per second. So now we have mass flows. We got everything to go. We got everything we need here. So essentially, the entropy balance. So we still don't know what the entropy balance of this thing is, but we know that 0 is the ds dt, right? Equals 0 because it's steady state. Let's see. Do we have any q? We have no q over t. dq over t goes to 0 because it's adiabatic. Plus m dot 1 s1 plus m dot 2 s2 minus m dot 3 s3. Right, and we know everything. Oh, plus of course the sigma dot, which is what we're trying to find. And so sigma dot is equal to m dot 3 s3 minus m dot 1 s1 minus m dot 2 s2. And we know all of these things because we looked everything up. So this ends up being 80 times 1.6718, which is S3, minus 66.32 times 0.5188, minus 13.68, oops, that's a point, times 6.5663. Sorry, I got some crazy decimal places going on here. But anyways, you get to the idea that the sigma equals 9.51 kilowatts per K. So this is definitely irreversible. Pretty highly irreversible. Which I guess we know. These pure mixing processes are pretty irreversible, meaning that they're really lossy. They're really easy though, from a physical perspective. I mean, all you got to do is you take high quality hot steam and mix it in with some water, and you get yourself some two-phase liquid, which is great for the boiler, as I said, for the steam power plant. So, anyways, this is how you do this problem. So you can see that we've developed the as I said, it's a two-equation class. Thermodynamics is a two-equation class. I mean, third if you count the mass conservation. But really, the equation, so if you just want to think about it in terms of three equations, the three equations are all in this problem. So 1 is here, 2 is here, and 3 is here. Right? So these are the three equations that you need for thermodynamics, pretty much. And then ideal gas law, but everybody knows the ideal gas law. So pretty much you need to know the energy balance and the entropy balance are the big two. Okay, so let's do another example. Let's do one more example before we quit. That example took a good amount of time, so we should get this one done just in time. Okay, so this one is an air problem. So we have air at 400 kPa and 980 K enters a turbine. So it's hot, pretty hot, at steady state, and exits at 100 kPa, 600 K, still pretty hot. Heat transfer from the turbine occurs at an average outer surface temperature of 315. So that's your heat loss to the environment coming through the body of the turbine. I mean, you could say the turbine's adiabatic, but probably that's unrealistic. Especially at these temperatures, at the rate of 30 kilojoules per kilogram of air flowing. So they give us the rate of heat transfer out. Kinetic and potential energies effects are negligible. Air is modeled as an ideal gas with variations in specific heat. It specifically tells us that we have to consider variations in specific heat. So this means that you just think to yourself, I have to use the tables, okay? The air tables. Determine A, the rate power is developed, and kilojoules per kilogram of air flowing, and the rate of entropy productions within the turbine per kilogram of air flowing. All right. So this is a good problem, actually. This will give us a lot of things that we need to know. Okay, so what's known? We have air, turbine. I don't know. Yeah, that's it. We just know it's an air turbine, okay? It's not adiabatic or anything. Find A, we're going to find the rate of power, the rate power The rate powers developed. That doesn't make any sense. Kilojoules per kilogram of air. Anyways, all right. So we need kilojoules per kilogram of air. So we need little w. Air flowing, kilogram of air flowing, but we need little w. B, because it's not per second. It doesn't say per second. Their entropy reduction, rate of entropy reduction of the turbine per kilogram, kilojoules per K. So we need sigma, not sigma dot. I don't think we're solving for sigma dot, are we? Let me look at my solution real quick. I guess we want sigma dot over m and little work dot over m. Well, little work dot is, never mind. Little work dot is a, it's kilojoules per kilogram second. Okay, fine. Let's just do that. All right, so now let's do some assumptions. One, we're assuming this is steady state. Steady state, we are, anything else? We have heat transfer is not adiabatic. Well, air is an ideal gas. Without the constant specific heat. So we're using the table. Okay, so if you make my diagram over here, it's a turbine. So we always draw a turbine like this sort of thing. And we always have stuff coming in and then out. So we have 1 and 2, and we have to make our control volume, of course. And we have Q. I guess we're going to call it Q dot. I don't know. We can call it Q dot, big Q dot. Okay, so we have some heat being lost. Heat from the occurs of 300 at the rate of 30 kilojoules per kilogram of air flowing. Okay, and then, let's see, what else? Oh, I forgot that we were going to have to also neglect delta KE and delta PE. Okay, we're neglecting kinetic and potential energies here. Okay, so now let's see, what are we going to do? So the analysis, so we're given 1 and 2. What are we given about 1 and 2? 400, so 1 is at, I'll just put analysis there. State 1 is at 409.80. State 1, and then state 2 is at 106.70. So we've extracted some heat. We've extracted some heat from this thing. Okay, so now and some work. So we got work coming out. Oh, do I put work in my? So we have. Of course, this thing has to make work. Okay. Yeah, I mean that's the whole point of having a turbine is to make work. Okay. Energy analysis. So here we go. So the first thing we're going to do is the first law. The mass balance is boring. M.1 equals M dot. So I'll just say boring. M.1 equals M.2 equals M dot. Okay. One inlet, one outlet. It's pretty boring. Okay. Let's see. We're ejecting heat. Maybe I just put this in here at 3.1. What is that? 315 K. We're rejecting heat, whatever surface it is. Okay, so let's go. The first law looks like this. 0 equals, we write it as big Q dot minus W dot plus M dot H1 minus H2. Okay, I don't like this. There we go. H1 minus H2. Now simplified, we end up getting, of course we want to do this all based on the mass, right? So we're actually W dot over CV. Let's put this as a big W, and I'll make this a little w, okay? Because that will make it little w equals Q plus H1 minus H2 because we divided by M dot. Let's see. Yeah. Get rid of that. Okay. So we divided by M dot, and that's what we got, okay? Because Q dot divided by M dot is little q. And W, big W dot divided by M dot is little w. Okay, so let's use table, A22. for air. So we use table A22 for air, and we get H1 equals 1023.25 kilojoules per kilogram, and S1 naught is equal to 2.9447 kilojoules per kilogram K. H2 is equal to H2 is equal to 681.14 kilojoules per kilogram, and S2 naught is equal to 2.5259 kilojoules per kilogram K. All right, so now we got everything. Remember that this means at standard pressure. Okay, now we have to do the pressure correction with it when we do it. So then we substitute, and then we end up getting little w is equal to negative 30 kilojoules per kilogram, because that's what we had here, 30. This was the heat, right? So work equals the heat, and it's heat out of the system, so it's negative plus 1023.25 minus 681.14 is equal to 312.11. Oops, let me get my camera out of here. Okay, kilojoules per kilogram of air flowing. All right, so we're going to kilojoules. So I guess they really want us to find here. Where's the find? I think they wanted this, little w and sigma dot over m. Okay, so here we go. So then we have the work. Oh, was that one of our answers? We had to power developed. Yes. Okay, so this is the power per unit mass. So this problem. So part B is now to find the entropy production. So the entropy rate balance is like this. So we'll just say second law gives us 0, because ds dt is 0, because it's a steady state process. Okay, you just got to remember that. Equals, we're just going to say q dot cv over t at the boundary, which is 315 as we said. Oops. Plus m dot s1 minus s2 plus sigma dot. Okay, so we want sigma dot over m dot. So what we're going to do is we're going to divide everything through, but we want to find s1 minus s2. So s2 minus s1 is equal to s2 naught minus s1 naught minus r bar over m, big M, molecular weight of air, natural log of P2 over P1. So this is the pressure correction we've talked about for ideal gas. Okay, so if we think we have everything we need here, we'll just put it in here. So what we need is sigma dot over m dot, which is sigma over m, equals minus q. I'm going to put it like this. I'm going to make it like q over tb, because that's the only heat transfer that's occurring throughout over the control volume surface, or the control surface, plus s2 naught minus s1 naught minus r bar over m, natural log of p2 over p1. And then that gets us to the final answer, which we want, is equal to, so this is minus 30 over 315, so that's the heat transfer leaving the system, plus 2.5259. Oops, this is really messy. Let's just try this again. I'm getting rushed because it's the end of class. 2.5259 minus 2.9447, which is S1, minus 8.314 divided by 28.97, which is the molecular weight of air, times the natural log of the pressure ratio, which is 100 divided by 400. Okay, so now let's see, do I have everything I need? Actually, put this parentheses here. Okay. So, anyways, we get this thing solved, and we end up getting 0.074 kilojoules per kilogram K for the entropy. So sigma dot over m dot. And that is the answer, I think, because we're assuming variable specific heat, so we look these up in the tables. And we end up getting the final answer. So yes, it's positive. So there are irreversibilities in our system. Okay, so hopefully that gives you an idea how to do these control volume problems. It's pretty easy. All you just have is a entropy in and entropy out term that you need to account for. And for steady state, then the ds term goes to 0. Whereas for the system, thermodynamic system, the ds term is what you're solving for, and the in and out is 0. Okay, so that's the only difference here. All right, so now we've got these both example problems, which I will post before tomorrow's lecture. And I think that's all I have, so please make sure to ask me any questions and keep me honest on the homework. I know I've made some mistakes in the homework, and I apologize about that, but it's good that people reached out to me quickly right after it's assigned, and then I change the assignment and everybody can do it. So usually by the time it's 24 hours before the assignment is due, I don't get too many people asking me about the assignment. It seems like it's been worked out. So I appreciate the people who are doing the homework assignment early, I guess is what I'm saying. Okay, great. I hope you had a great weekend, and let's start off a good week this week, and I'll see you again on Wednesday.